Welcome back to ECE 442-542. Just as a reminder, a couple of weeks from Wednesday is your first exam. I think that's a Wednesday, the 12th of February. Just to keep you thinking and keeping you ready for what's coming, we'll have one more homework assignment, and that one will be due a week from Thursday. Your first homework assignment is due this Thursday. And that means that we'll be covering the material we're covering now and some Z transforms for the first exam. That's where we're headed, or that's the idea. To get there, we have a long list of topics to cover today. We'll start with a block diagram in discrete time, which will be based on the difference equation, the second order linear difference equation that we introduced last time. We'll look at that in the time domain, which is an all delay block diagram. And if we label that diagram appropriately or properly, that will nicely allow us to write down a state space representation from that block diagram, a discrete time state space representation. We'll then look at how we can also display that same information in the frequency domain in a frequency domain block diagram, where now instead of these 1 over s's that we've had maybe in the s plane for continuous time, now we'll have 1 over z's, or z to the minus 1, in the z domain, or the frequency domain associated with discrete time systems. The block diagram structurally will look the same, and we'll be able to find the transfer function of our system from that block diagram. And I think in homework 1, you're having to find some transfer functions there in terms of transfer functions themselves within the block diagram, but hopefully it will be similar to what we'll talk about today. We'll look at the interpretation of the complex variable z. It maybe has a little bit more intuitive, it's maybe a little more intuitive than the S in the Laplace that you've been thinking of or using. But you can think of Z now as an operator, in a way, but we'll then do some mapping between the S plane, that's a complex plane, and the Z plane, which is also a complex plane, and we'll see what that leads to, and in particular, that will illustrate why now we're focusing or concentrating on the unit circle in the z-plane for stability versus the entire complex left half plane in the s-plane. The entire left half s-plane maps into this smaller region in the z-plane which determines stability, and that's the unit circle. We will also talk about when we're going from the S-plane to the Z-plane, we might need to select a sampling period, capital T, or a sampling frequency, which is related to the sampling period, capital T, and the sampling frequency in hertz. So we have the sampling frequency in radians per second, we have the sampling frequency in hertz, or cycles per second, or we could think of the sampling period, which is reciprocally related to the sampling frequency f sub s. And that's what we're going to try to be getting comfortable with. If somebody simply asks you to select a sampling period, capital T, then a very nice rule of thumb is to just say, oh, I need to sample 30 times the closed loop bandwidth. And that will make more sense, but right now I want you to just focus on that rule of thumb. If somebody says, oh, pick a sampling period, you'll say, oh, I need to make that 30 times the closed loop bandwidth of my system. If you know what that is, what omega sub c is, then you can immediately find omega sub s, and from this earlier equation or expression relating the sampling period to the sampling frequency, you can solve for capital T and obtain the sampling period, which really gives you the sampling frequency, based on knowing the dynamics of the closed loop system, or the speed or the bandwidth of your system in the closed loop. We'll be talking about open loop and closed loop. We usually are speeding things up in the closed loop That's why this is what it is, the closed loop bandwidth. This will hopefully start to make sense as we move through the semester, but we're getting some of these ahead of time because you can use them right away. We can then, once we have this idea of Z and what it looks like, or that it corresponds to in the time domain a delay of one sample period, we can now Z transform the difference equation like we could Z Laplace transform the differential equation. And we can now quickly go from a linear difference equation into a frequency domain representation and find a transfer function in terms of this complex frequency variable Z in comparison to the S that you've maybe done before. Then we'll sort of say, where can we use this, or what's going on? Let's then talk about the definition or define the Z transform relative to what we've done for the Laplace. Hopefully we're sort of remembering the Laplace transform definition. And then we'll look at transforming some common waveforms. The unit pulse, now that's not an impulse that's infinitely tall and has an area underneath it of 1. Now we simply have a pulse that's amplitude 1 right at time n equals 0, if n is our index on the time. That's a little easier to think about than this impulse response. Now I'll just call it the unit pulse, and we'll have a unit pulse response if we applied that to some system. We'll look at then the unit step, exponentially damped, maybe exponentially damped sines and cosines, and what those look like in terms of their Z transform representation and how we can maybe go back and forth. So we'll at some point start to be comfortable with Z transforms and inverse Z transforms, allowing us to move back and forth very easily between the time domain and the frequency domain. Let's then get started wherever we set our map started. Oh, I've got too many maps floating around. We're mapping, and this is my roadmap for today's lecture. First thing that we'll do is we'll start with a block diagram based on what we had before with this linear difference equation. Let's then look at a block diagram, and I will call these, if they're in the time domain, an all delay block diagram. And I'm going to actually introduce a new variable. Maybe I called it Y or X before, but I'm going to try to reserve X's for my state variables, so I'm going to change it up to a Z. Ooh, and that's not the... I thought that was a good choice. Now I'm second guessing that because we have the Z transform, so maybe Z is going to confuse you, right? Ugh, what's a good one? And W's, I'm terrible at making W's, but let me try. So let me say that this is now W of n plus 3W of n minus 1 plus 2W of n minus 2 is equal to the reference input R of n. And that left-hand side, this should look similar to what we had the last time. If you can remember, well, this is our first Monday lecture, so you don't have to remember a week ago. This is just a few days ago. Right? Our last lecture was on a Wednesday. Now we really sped things up. Now we're lecturing on a Monday. Then we'll see you again on Wednesday. Hint, hint. What? This is a non-homogeneous difference equation because we have a forcing function or a input driving, and our input now is some generic signal R of n. But W is, let's say, the variable that we're using to describe that behavior in the time domain, whatever that might represent. Let's now solve that for the highest index, time index, which is W of n. So this is now W of n is equal to R of n minus 3W of n minus 1 minus 2 W of n minus 2. Now you'll have to keep me honest and try not to go back to z's and x's, and so I've now changed to w's. But how many delays are we going to need for this particular system dynamics? 2, right? We have an n minus 1 and we have an n minus 2, so it's pretty clean that, or clear, I hope, that we need 2 delay elements. Let's then put those in. And if I now introduce my w of n right there and delay it once, what's going to come out of that first delay? So this will be one time period or one sample period in the past. And likewise, here is w of n minus 2. And now I can actually connect this up so that I can implement that second order difference equation in the form of a block diagram. If I, build up w of n as a linear combination of the forcing function r of n and these delayed versions of w, meaning w of n is some r of n, and it's also minus 3 times w of n minus 1, and it's minus 2. I was trying to keep it all on one screen. And that's now another way of basically expressing this second order difference equation in the time domain through an all delay block diagram. Somewhat like an all integrator block diagram for the continuous time setting. Now we want to take that into a state space representation. And the only thing you have to remember now is we need to define state variables. It's second order, so we would expect to have a second order state space representation, and the strategy is simply to label the outputs of your delay blocks as state variables. And hopefully it's clear that somebody could label this as x sub 1 and this one is x sub 2, or just the opposite. So a state space representation is not unique for a given system dynamics. Let me now just label. So here's what I'm wanting to do. Is create this state space representation. And to do that, I can define the outputs of the delay blocks as my state variables. Meaning I'm going to now label this one, just because a lot of times that last one coming out is our output. So let me just call that x sub 1 of n. And this one is x sub 2 of n. And now I can write my state space representation. I should end up with 2 first order difference equations that are coupled to each other. Meaning, what is, now I've made it disappear. I'm a magician here, but I can make it reappear. So come back, all right? Now, what is x sub 1 of n plus 1? In terms of, you need to write these one time period advanced state space variables in terms of x1 of n, x2 of n, and r of n. Now I'm trying to express x sub 1 of n plus 1 as some linear combination of undelayed state variables or unadvanced state variables and the input R. I'm looking for x sub 1 of n plus 1. Well, that's right here, isn't it? In terms of states, that's exactly what I called x sub 2 of n, meaning my very first order difference equation is x sub 1 of n plus 1 is simply x sub 2 of n. Is it clear where that came from? This is now right there, x sub 1 of n plus 1. And that's exactly the same signal as x sub 2 at n. And so that's all I've done is I've written that down. Now I need another one. I need one more difference equation, and that second difference equation is going to be x sub 2 of n plus 1. But that is right here. And I need to express that as a linear combination of x1 of n, x2 of n, and r of n. And hopefully you can see that the output of that summing junction is equal to the inputs of that summing junction. Or x sub 2 of n plus 1 is now equal to minus, well, it depends on what I want to do. Maybe I'll write it in the correct order. I could just cycle through here, but I want to write x1 first. So I'm going to pick this one up, then I'll go back and pick this one up, and then that one, if you'll allow me to do that. But you can write these in any order. It's just you need to put them in the correct location when you put them in the matrix form. But I have minus 2x sub 1 of n minus 3x sub 2 of n plus r of n. And that's now my state space representation, and I could define an output. I'll do that in a minute, but let me put this into matrices, meaning now I have a column vector of state variables advanced by 1 unit of time. Here's x sub 1 and x sub 2, both at time step n plus 1. That's equal to some matrix, and that system matrix is always going to be square because I have 2 outputs and 2 inputs to that particular matrix. And now what are the dimensions on my input matrix? The matrix that scales R, it's now TWO tall and 1 wide because I only have the 1 input R of n. I now need to figure out what goes into these 6 element entries in the A matrix, or I may call it the phi matrix in the discrete time state space. That's this system matrix here, and this 2 by 1 input matrix in the difference equation state space or discrete time state space representation. The top row is maybe too easy, and so it's hard, but all we have to do is pull off x sub 2 at time step n. We do not need any x1, and we do not need any of r to build up that first relationship or that first equation. And then the second equation, we have a minus 2, a minus 3, and a 1. And I might at some point call this a matrix phi, capital Phi. I might call this gamma. I don't know, I just want to throw around some Greek symbols here. So we have phi and gamma. You can put this on your shirt or text it, I guess, when we're doing SS and TF, state space transfer function. We'll have a phi and a gamma. That may be kind of hard to find depending on your phone, I guess. Who knows? Now, what if we call this the output, y at time step n? Coming out of that block diagram, now we're saying y of n is some linear combination of the states plus some direct feed-through term that scales the input R. And if y of n is simply x sub 1 of n, I could add another summing junction here and make it some linear combination of x1, x2, and a direct feed-through from the reference input R if I wanted to make it a little more complicated. Here I chose an easy output. Y of n is now simply going to have to pull off x sub 1 and have no direct connection with the input R. And that's now my state space representation, and maybe I'll call this, oh, I just like to play with you, H and J, mixing Greek and alpha characters, right? Or English characters. Just so that we start to think about dynamics, the system matrix phi is actually describing the open loop. We haven't introduced any kind of feedback. This is the feedback that's in this block diagram is inherent to the difference equation or the system itself. We haven't now tried to go in and measure these and feed those back to change the dynamics of our originally given system. And if we wanted to find the dynamic behavior of this system in the open loop, it's really represented by this system matrix phi. And we might be interested in the eigenvalues of that. That's actually going to be the poles of our system in our transfer function, so that we can connect to all these concepts from linear algebra. Maybe you're taking Math 10, maybe you've already had Math 10. You need to be able to connect all of these with what we're doing. So let me just give you that information. Notice that the eigenvalues of our system matrix, which we were calling phi, equal -1 and -2, which were the roots when we were solving that homogeneous difference equation. We found those to be the roots, -1 and -2, but that's also of the characteristic equation. So if we want the eigenvalues, we now look at the determinant. That's what these vertical lines mean. Determinant of this matrix lambda I minus phi. Phi is 2 by 2. Lambda is a scalar, but I has to be compatible with phi, so it has to be the 2 by 2 identity matrix. This lambda I minus phi is now the determinant of lambda times some identity matrix minus the phi matrix or we now have lambdas on the diagonal coming from that lambda I, and we subtract that phi so that we now have a matrix lambda and nothing in the 1, 1 entry. We subtract -1 in the 1, 2 entry. We have a subtraction of -2, or we get a 2. And then we have a lambda minus a -3. And we want now the determinant of a 2 by 2 matrix, which I'm hoping you remember. That's just the product of the diagonals minus the product of the off diagonals, which is now lambda times lambda plus 3 minus a minus 2, which gives us a plus 2. This now says that that characteristic equation found by finding the eigenvalues of this state space representation is given by the roots of, or the values of lambda that solve, lambda squared plus 3 lambda plus 2 equal to 0. So there's our characteristic polynomial. Our characteristic equation is when we set that equal to 0. Now we've connected these ideas that we talked about last time, which was this solution of a homogeneous linear difference equation with a state space representation and the eigenvalues of that system matrix, and that's now the same as that roots of those of that polynomial.
So does that mean that this is unstable?
So the question, or maybe the statement, was, does that mean this system, if we went back and somebody gave you this system and said, oh, here's a state space representation of a system, maybe they gave it to you immediately in this state space form, and they say, is it stable? You would say, well, I need to check the eigenvalues of my system matrix, which the system matrix is phi. And knowing now what we know, we found those eigenvalues, and based on what we will maybe do in just a little bit, we will convince ourselves that if any of those eigenvalues have a magnitude, so if they're complex, you find the magnitude of those complex numbers. If any of their magnitudes exceed the unit circle, then they're going to go unbounded in time, and it would be an unstable response, and that's what this guy is saying. This one's right on the unit circle, so I wouldn't like that one anyway, because that one's just going to go back and forth, back and forth, back and forth, and not decrease in value as time evolves. It'll just sit there and oscillate back and forth. And it's pretty high frequency oscillation. If it was just this by itself, you would be changing sign at each time step, and that's probably not a good thing, depending on what you're wanting to do. Now, that was all done in the time domain, and you guys are engineers, so you need to be comfortable working in both domains. You need to be able to sort of throw things back and forth between the time domain and the frequency domain. Let's put this into the frequency domain by means of the block diagram. We want to analyze discrete time systems not only in the time domain, but also in the frequency domain. And we'll do that today by using this connection in the block diagram that we are going to establish right now. Do you remember what we replaced the integrals with in our all-integrator block diagram when we were in the continuous time setting? We just replaced those with 1 over s's, didn't we? Well, now what we're going to do is we're going to replace these delays which this is now in the time domain, with z to the minus 1. And this z to the minus 1 is our complex frequency variable. Meaning, if we just, this is why I said you might want to attend an art class, right? Now all you have to do is sketch. You just have to draw. You've got this all delay block diagram. All I'm asking you to do is replace the delays that are time domain operators with a frequency domain operator, which is z to the minus 1. And everything else stays the same, except now all your signals are not indexed with n's, they're indexed with z's. Just like when you Laplace transform, you end up with capital X of s, maybe. Now our signals might be capital X of z. It'll be in the z domain. The z transform is really what it's representing. But let's now draw this or sketch this in the frequency domain or the z domain, meaning now we can replace our delay blocks with z to 1 over z's, or z to the minus 1. And now here's where I really get angry, if you mix time domain and frequency domain. So here, to avoid that, I'm going to capitalize that and say that's r of z. That's the z transform of my time domain reference signal. Here's a minus 3. And here's a minus 2. And these signals, the directions are important. So those are one-way links. I can't go back against that arrow. And I was calling this my output. So if that's the output in the frequency domain, then I'm going to call that capital Y of Z. Now, just to connect this with what you're doing, or maybe you've already finished it, so you should feel comfortable with this if you've already done your homework, let's call this an error signal. And if you're doing block diagram manipulation, sometimes it's easy, or maybe a little more straightforward, to always kind of play with or work with outputs of summing junctions and write all of your other signals in terms of those expressions. Now, if you need to keep track of the inputs that might be coming in from different locations, we have a disturbance coming in the input, or in the homework, we have some noise coming in. If you can keep track of all of those, you're fine, but you might want to write your equations in terms of the E. And then we'll just sing, okay? When we sing, what is that? That's a signal, isn't it? And so you need to make sure that you're keeping track of signals and systems. And there's a difference, meaning if you have a Y of Z, that's equal to a signal, isn't it? It's not going to equal to a system. So when you're writing these equations, if you wrote Y of Z, it needs to be expressed in terms of some combination of Z's and minus 2's and an E or an R or both. But it has to be a signal. Let's do some block diagram algebra. This is maybe what you did in 6th grade middle school. Did you do some algebra? You probably did it with block diagrams, I'm guessing, right? Wow, tough crowd. Block diagram algebra. What I said is I'm going to try to write these in terms of the signals coming out of my summing junctions, and I only have one summing junction, so I'm going to try to write an equation in terms of E of Z. Well, that's just the sum of all of those coming into that junction. One of those signals is R of Z. So now I have a signal is equal to a signal. That seems to be consistent. This is just like when you're writing circuit equations. You can't be adding voltages and currents, can you? If you've got a voltage equation, all of those terms need to be voltages. Or if you're writing KCL, they all need to be currents. So don't be writing I's equal to V's. Again, that's something that you don't want to be doing, right? That didn't come out in the audio, so you'll just have to imagine that when you're listening to this somewhere. Where were we? Oh, we need to come back and Now I want to express that signal. Well, that signal is, if I follow my path back, it's minus 3 z to the minus 1 e of z. So I'm going to just write it that way. So that highlighted yellow signal is now minus 3 z to the minus 1 e of z. And just so we can kind of get used to maybe or maybe not chasing our tail, let's say that this next one, just so we do it different, I'm now interested in that signal. I'm just going to call that minus 2y. You can see that far back, right? So now I'm going to say, oh, that's minus 2y of z. So all of these are some system's trivial here. It's a 1, isn't it? Times a signal. So a system times a signal gives me a signal, and that's part of E. I have another system scaling E, and I have another system scaling Y. So now I have all these signals that are related to each other, and that's consistent, and a consistent equation. But I can express Y in terms of E. That's just going through two of these z to the minus 1 operators in cascade, isn't it? So I'm trying to really find an expression maybe between r and y, but initially I'm going to get this intermediate result relating E and r. Y of z goes through one z to the minus 1. It actually goes through another before it gets to E. Or this is now z to the minus 2 e of z. And that's now what I'm going to use to get rid of y, and now I have one equation that only contains e's and r's, and I can solve that for E. E of z is then this r of z minus 3z to the minus 1 e of z minus 2 z to the minus 2 e of z. Are we okay with where that came from? And now we just have e's and r's. I can get all the e's on one side and all the r's on another. And I'm just going to go ahead and combine those now. I know you guys can do the math since you've been doing this since 6th grade, right? So this is now 1 plus 3z to the minus, plus 2z to the minus 2 e of z is equal to r of z. Or I can now solve that for e of z, and if I wanted an equation or a transfer function between the reference input r and the error signal coming out of that summing junction, e is not just r, is it? It's some linear combination or filtered version of E. So now we have this equaling 1 over 1 plus 3z to the minus 1 plus 2z to the minus 2 r of z. So if we wanted it, we could claim this is a transfer function. It is between the reference input r and the error signal E, where that error signal E is the output of that summing junction. And there's a transfer function. And you could now, well, we'll do that in a minute if we want, but we could find now a difference equation. We could take that back into the time domain by cross-multiplying and remembering what z to the minus 1 is in the time domain. That just corresponds to a delay of 1. But before we do that, we really wanted a transfer function between r and y. But y, we know how to describe in terms of E. We're done, right? Put a fork in it. All right. I shouldn't have said that. Now I'm hungry. And I don't have any pies on my tablet right now. Then I'd really be hungry. But now we have y of z is equal to z to the minus 2e of z, but that's just in terms of r. That's now a transfer function relating the reference input r to the output y in the frequency domain. That's now a g of z if we wanted it. Maybe you're not used to seeing that in terms of z to the minus 1, z's to negative powers. Well, we can change that just with some algebra. We could say, what if I factor out a z to the minus 2 from both the numerator and the denominator? Then I have a 1, and downstairs I have a z squared. Z minus 2 to z squared will give me 1. That's the first term, plus 3z plus 2. And what's this? That's just 1, isn't it? So that goes away, and now we have a transfer function between the reference input r and the output that we selected to be y, and this is now our system's transfer function. Just the piece that's inside the square brackets. And that's a second order transfer function, which is consistent with our second order difference equation. Now, like I said, if we wanted to, we could take this back. If somebody now gave you this and they said, can you simulate this on a computer, or can you put this into a microcontroller and do some filtering? Maybe this represents a filter. It's not a very good filter because it's banging and blowing up, isn't it? It's unstable. But you could have a filter given by g of z between some input and some output. Maybe you created this g of z to actually be a low-pass filter. And now you want to implement that, and somebody says, oh, here's your transfer function. Have fun. So you go, that's fine. I can create a difference equation that I can then just code into my microcontroller or my computer, that if you give me a string of values coming in that you want filtered, I can number crunch and give you the output that's a filtered version of whatever you started with, based on this system or this filter, whatever this transfer function represents. Let's then go back from the frequency domain back into the time domain and create a difference equation for this representation. Observation. And let's, since we are going to be doing this in a computer, let's use the first form of that transfer function that's written in terms of, in the time domain, delays, z to the minus 1s and z to the minus 2s in the frequency domain. We now know that y of z is this z to the minus 2, 1 plus 3z to the minus 1 plus 2z to the minus 2 r of z. If we simply cross multiply and make this just one equation, we now have 1 plus 3 and no ratios and z to the minus 1 in the frequency domain that corresponds to a unit delay in the time domain. So really we're inverse C transforming now, if you didn't know it. Now we can go back into the time domain, and capital Y of Z, if we want it in the time domain, what is it? Capital Y of Z. That's the hard one. It's so easy, it's hard. That's just little y of n, isn't it? So now 1 times capital Y in the time domain gives us y of n. What's the next term? 3 times a delayed version of y of n, and it's delayed by 1 plus 2 y of n minus 2, and that's equal to r of n minus 2. We created a y that wasn't quite w. W is what we started with, and w was immediately tied to r. But we picked the y to be 2 delays away from w, and that's why this r looks different, or it's a delayed version of what we had to begin with. But this is now a linear difference equation that's second order, and you could implement this in your controller. What do you have to do? If you need y of n, you just add up 3 times y of 1 time step before, plus 2 times y the time step before that, and plus r 2 time steps before y. And you can do multiplication and addition in your code, and now you have a way of filtering this input r to produce an output y. And that might be a filter, a low-pass filter. Maybe it's a band-pass filter. And you could make it a bigger order if you wanted to. But now you're capable of doing that. Now that we've been throwing these z's around, let's try to get a feel for interpreting that or understanding that a little bit more. So now let's look at this interpretation of z. Always keep in mind that z is a complex value. It's a complex variable. Now, what I'm hoping to do is tie this in with what you already know. And I'm assuming you're experts with Laplace. Let's then recall the continuous time case. And the S domain. If we're in the S domain, what I'm trying to understand is a frequency domain representation of delay. Do you remember the definition of Laplace, just so we can write it down? Some integral, wasn't it? We simply weight our time domain waveform over all time, 0 to infinity, scaled by this complex exponential, where that complex exponential basically gives us the frequency content or the S domain content in that time domain signal, x of t. So this is now our frequency domain version of x of t. What happens, do you remember this property. How do we relate a delayed version of x to the Laplace transform of little x of t? You guys don't dream about this all the time? It's just not right on the tip of your tongue? I thought maybe somebody might wake up and go, what's he? Oh, yeah, the delay. I've got that. I know what that is. What is that? You're getting there. That's e to the minus the delay times s times x of s. So if we wanted to know what's the impact of a delay of length t sub 0 in the frequency domain, that's represented in the s domain as e to the minus t0s. This is the impact of our delay. Now, we want to specialize that to a particular length of delay. We know T naught is going to be one sample period when we're dealing in discrete time. So we're going to force T naught to just be one sample period of delay. If that T naught is one sample period, then a one sample period delay what did we call that in the z domain? Z to the minus 1. And if we set that equal to what it is in the s domain, we're going to have a relationship between s and z. So that now we have that should equal e to the minus t sub 0 s, where t sub 0 is one sample period of delay. Now, little t sub 0 is kind of tedious to keep track of, so let's just call it capital T. We'll just agree to that. So that now we're saying that z to the minus 1 is e to the minus t sub 0, little t sub 0, which we're saying is now capital T. Now we have a way of relating s and z. Anything we knew before about s, if we had an s, we could now put it through this relationship and find what it is in the z domain, if somebody gives us the t, the capital T. So t is the sample period. Well, we've got some negative exponents. Let's get rid of that on both sides, right? We could just put that's 1 over z is equal to 1 over e to the ts. Well, the numerators are equal. Those are just 1s. So the denominators must be equal, meaning that also says that z as a complex number or variable is e to the ts, and s was a complex number. This is now our relationship between z and s. And if you wanted to think about it, if z to the minus 1 is a delay, z, its reciprocal, must be an advance. So z is just an advance of one sample period. Right? Okay. Well, as long as we can, so the comment was, and maybe I shouldn't repeat this, but that's hard to implement in the real world, but we can define where we draw our time 0, right? So we could sort of say, oh, well, that's just advanced one time step from this value. Well, I haven't started yet. Here, that's another advance. So as long as you define where you start, you can write this in terms of advanced relationships or delayed relationships. It really doesn't matter. So it's nice to know that z and z to the minus 1 are advances and delays. Z is a complex number. That we will use as a frequency domain operator for discrete time systems. Let's just get a feel for your homework assignment. You're having to play with poles that are associated with continuous time domain systems or signals. And you know that those poles are somewhere in the complex S-plane. What if, let's just look at where a particular instance of a pole in the S-plane, where that might map to in the Z-plane, and what we can learn from that process. This example then is going to try to illustrate the mapping from the S-plane to the Z-plane. To give us something to think about, here's our complex S-plane. Real is horizontal, imaginary is vertical. Maybe we pick something, suppose S now is minus 3 plus J2. And this is a complex plane. It has a real axis and an imaginary axis. We're going to map that into the Z-plane, which is also another complex plane, a separate complex plane that also has a real axis and an imaginary axis. And we want to know, where does that guy go relative to the Z-plane? So we're not finding Waldo. Where's Waldo? We're finding Z. That's more interesting anyway, right? So now find Z in the Z-plane. What are we going to use? So hold that thought. Somebody said, what's T naught? Or what's the sample period? That's what we have to figure out or create. Let's now realize, though, that we're using Z is equal to e to the st, right? So Z now is equal to, for our particular choice of S, that's e to the st, and that's e to the minus 3 plus j2t. Well, exponents, we can distribute that t among the two pieces in the exponent, and we can basically break that z into two pieces, meaning z is now equal to e to the minus 3t, and it's also e to the j2t combined. And if you don't feel warm and fuzzy about that, think of that this way. Z is now r e to the j theta sub d, with r equaling e to the minus 3t and theta sub d is 2 times capital T. Where T, we haven't yet decided what that's going to be for this particular mapping, but that's our sample period. Meaning, we now have this complex number is just a magnitude at some angle. And you can draw a vector that has a magnitude and an angle relative to the horizontal real line. Our angle is defined that way, where positive is counterclockwise. You tell me what r is. Well, that's just e to the minus 3 capital T. Capital T is a positive number, isn't it? So this is going to be a negative exponent. Let's make some observations about what we have. First, if I looked at the magnitude of r, that's the magnitude of e to the minus 3t. Do you believe me that that's always less than 1, no matter what t is? And if you don't, then let's just convince ourselves. Meaning, let's just draw a graph. Suppose we now look at the picture for r, which is e to the, let me just forget this, and let me just say that this is going to represent the magnitude of r, which I'm just going to say is e to the x, and I'm going to say x is the horizontal line here. This is not the complex plane. This is just a relationship between x and e to the x as far as a value. So this is the exponent. And I hope, maybe I should have done this. What's e to the 1? Do you remember what e is? 2.7 roughly, right? So e to the 1 is 2.7, a little under 3. So I can draw that here. That's right here. So here is e to the 1. Just making sure you guys were awake. Okay, here's 1, 2. Is that better? What's e to the 2? 2.7 squared. It's a little less than 3 squared, so it's a little under 9, isn't it? But it's bigger than 2 squared, which is 4. So we're between 4 and 9. Better be bigger than 2.7, obviously. So it's, what did I write it down? It's 7.39, 7.4. I can't even put it on here. It's really going up there in a hurry, isn't it? So it's way up here. What's e to the 0? Here's 0. That's 1. Do you remember what e to the minus 1 is? What do you get to in one time constant? How much of your response? 1 over e. So now it's 1 over 2.7, right? Which is a little bigger than 1 over 3. So it's a little bigger than 0.33. It's 0.37, isn't it? So this is now 0.37. That's e to the minus 1. What's e to the minus 2? 0.37 squared, right? It's a bit smaller, 0.135. So that's down here. E to the minus 3, even smaller. E to the minus 4, e to the minus 5. After 5 time constants, this is less than 0.01 in value. And what have we done? That's supposed to go up really fast, so maybe this is I'll erase it. Do you see what happens when we transition and get a negative exponent? This is when e to the x is equal to 1, isn't it? Here's where we have negative exponents, and what's that value? It's always less than 1, isn't it? That's why I could claim e to the minus 3t is less than 1. It had a negative exponent, so I know its magnitude is less than 1. This is then the negative exponent. And this is the positive exponent. Is that okay? So now anytime you have a negative exponent with e, you know your magnitude of that complex number is less than 1. What does that tell us? Well, now if we generalize this a little bit and say, oh, our complex variable s, whenever it's negative, it's in the left half plane, that will give us a negative exponent, and we know that all of those negative exponents are going to give us a magnitude less than 1. Or values of our complex frequency variable s in the left half plane, maybe I should say what plane it is because we now have multiple planes, left half s plane, map to values of z where? Now, if you give me a point in the complex s-plane that's in the left half plane, it has a negative real part, doesn't it? So it's going to be an e to the minus something t. An e to the negative something t as a magnitude is going to be below this line. So it's going to be in here, isn't it, value-wise? So now I'm concentrating on a magnitude. The angle of it could be anywhere, but the magnitude is less than 1. That's where this unit circle comes from. Now I know that if I have a pole in the left half s-plane, it's going to map into the unit circle in the z-plane. Map to values of z inside. Boy, my printing is getting, I didn't even improve much. Inside the unit circle. There's 2 observations. What else did we see? We found that the angle of that complex number in the z-plane is 3t. And that angle, it's in radians, depends on whatever we pick for capital T. So if this was our z-plane, we now know that we've gone out some distance r. If we were in the right half plane, we know this r would be bigger than 1, and this angle is now 2t. Oh, what if you guys, I ask you to keep me awake. This should have been 2t, right? For our example, that was J2. So this is 2t, that's 2t. Let's see if we can figure out what t might be. Do you remember what I claimed we were going to use before? Our rule of thumb for selecting t. we select t, the sample period, to be 30 times the closed loop bandwidth. Is somebody remembering Nyquist? If you remember Nyquist, what was Nyquist factor? What was the factor in Nyquist? If I gave you a frequency and I said, how's that relate to Nyquist? You would double it, wouldn't you? Now we're taking it by 30. Well, if we're controlling things, we need to be a little bit more precise than just keeping track of information. We need to keep track of the shape of these curves. So we need to make sure that we're sampling much more quickly than Nyquist would tell us. Nyquist just says, we'll keep the information. Well, we need more than just information. We need to keep track of what it's doing. So that's where that 30 is coming from. Now, what if in our particular example, let's say that we suppose and here I'm just pulling this out of thin air. I'm just giving you a closed loop bandwidth for this particular example. Suppose we want a closed loop bandwidth, and you'll get better at determining what that needs to be, but for now let's just say that it's 5 radians per second, i.e. that's what we were calling omega sub c. If our closed loop bandwidth is 5, what's our sampling frequency? And we said that needs to be 30 times omega c. Or in this case, that's 30 times 5. Bless you. So this is now our sampling frequency of units radian per second. This is also a sampling frequency. But its units are different. It's in hertz. And t is our sample period. And note that it's reciprocally related to our sampling frequency in hertz. F sub s is 1 over cap t. And now we want to make 2 pi over t equal 150 to find our capital T. So we just solve for capital T in this relationship. Therefore, capital T is going to be 2 pi over 150, which we can always make capital T smaller, and 3 is smaller than pi. There's my pi, but we're about out of time, so I can start thinking about pi now, my dessert, right? So don't tell anybody that I'm thinking about dessert before the main course. So now we have roughly 2 times 3 over 150. This is what used to make my Engineering 102 class really nervous, is approximating. They would go, we came to the university to be precise and accurate. I said, you just need to be able to get a good feel of what's going on. Let's just make some approximations. All right, so now where are we at? or 2 over 50. That's just 4 over 100, or 0.04, or t is 40 milliseconds. Or f sub s is 1 over t or we're sampling at 25 hertz, which isn't very fast, is it? But it's still 30 times the closed loop bandwidth of 5 radians per second that we started with. So I'll let you figure out where z ends up before our class on Wednesday. And whether or not I'll tell you or not is another story. But please make sure and look at your homework so you know what we're doing.